Right now, I mean, there are solo developers literally working out of their bedrooms who are pulling in like $300 an hour,
Yeah, it's crazy.
building the exact same enterprise AI tools that Silicon Valley giants are spending billions on. And the wild part is, they aren't doing it with PhDs. They don't have massive server farms in your
Right,
closets.
definitely not.
They are doing it by uh, basically popping the hood of open source language models, getting their hands dirty with the underlying architecture. Today's deep dive is really a masterclass on how you can transition from just being a passive consumer of AI tools to an active builder.
Because honestly, it's arguably the most profound shift in the software economy we've seen in a decade.
Hmm.
The barrier to entry it's completely dissolved. But there's this massive knowledge gap. Companies are just desperate for people who don't just know how to type a prompt into a chat interface.
Yeah.
They need people who can actually construct the underlying infrastructure.
Right, like optimizing weights, setting up vector retrieval systems, all that stuff.
Exactly. Reducing API latency, the whole back end.
So let's unpack this. Because to actually build that infrastructure, you have to understand the fundamental physics, if you want to call it that, of how these models operate.
Right.
We have to move past this illusion of a chatbot, thinking, and look at the mathematical blueprint. So let's talk about the architecture introduced by that famous paper, Attention is All You Need.
Ah, yes. The shift from recurrent neural networks, or RNNs,
Yeah.
to transformers.
Exactly, which is basically the engine room of all this.
And it was an absolute watershed moment. Because with the old RNNs, the architecture read text sequentially. It processed one word at a time, left to right, just like how we read a book.
Which sounds logical, right?
It does, but the problem there was the vanishing gradient. Basically, by the time the model reached the end of a long paragraph, the mathematical influence of the first few words had essentially decayed to zero.
Oh, wow. So it would literally forget the beginning of the sentence.
Exactly, couldn't hold the context. But transformers, they threw that entirely out the window by processing massive sequences of text in parallel, all at once.
Right. But before it even processes that text in parallel, it has to digest it, right? And here's where it gets really interesting to me, because we're looking at tokenization, and it's not just like a simple word split.
No, not at all.
I was reading up on algorithms like byte pair encoding, or BPE, and that's what a lot of the major models use over older systems. BPE doesn't just look at whole words, it actively handles these weird out-of-vocabulary anomalies.
Yeah, the mechanism behind BPE is fascinating. It actually starts by treating every single character as its own token.
Wait, really? Just individual letters?
Individual letters, yeah. And then it iteratively scans the training data for the most frequently occurring adjacent pairs of characters, and it merges them into a single new token.
Okay, I see.
And it repeats this merging process thousands of times. So common words like the or apple eventually become single tokens.
Right, because they show up so often.
Exactly. But if it encounters a completely bizarre, newly invented slang term, it doesn't crash. It doesn't throw like an unknown token error.
Because it just falls back on its subword or character level tokens to represent that new word.
Spot on. It's incredibly robust because it builds a vocabulary based on statistical frequency rather than relying on a static dictionary.
That makes total sense. And once you have those tokens, you have to map them into a geometric space using embeddings, which is basically mapping conceptual meaning into high-dimensional vectors.
Yeah, it's pure geometry.
I always try to visualize it as like a massive multi-dimensional library where books with similar themes are physically placed closer together.
That's a great analogy.
But it's not just grouping them, right? It's the relational math that blows my mind.
Oh, the spatial relationships hold actual semantic value. Like the classic vector arithmetic example, everyone uses this one. You take the vector coordinates for king, you subtract the vector for man, and you add the vector for woman.
And because of how the model has mapped everything out in hundreds of dimensions,
the resulting coordinates land you almost perfectly on the vector for queen.
it's literally doing algebra with pure concepts. It's wild. But, okay, here is where I want to push on the mechanics a bit.
Yeah.
Embeddings give us the spatial definition, sure. But the actual engine of the transformer is the attention mechanism. Now, I know it calculates the relevance of words to each other, but if the attention mechanism is the magic that decides which words matter most, how does it actually weigh that importance compared to, like, how a human brain instinctively reads a sentence?
Well, mathematically, it executes that across an entire document simultaneously, using a system of queries, keys, and values, often abbreviated as QKV.
QKV, right.
Imagine you are at a crowded cocktail party. You are the query looking for something specific. Let's say a conversation about artificial
Oh,
intelligence.
yeah, I'm the query.
Right. And everyone else in the room is holding up a key, which is basically a brief summary of what they're talking about. Your brain computes the dot product, the mathematical similarity between your query and everyone's key.
So the model is constantly calculating a similarity score between every single token in the sequence against every other token, all at the same time.
Precisely. And once it finds the keys that best match your query, it extracts the value, which is the actual substance of the conversation.
Got it.
In a transformer, every single token generates its own query, key, and value simultaneously. Through matrix multiplication, the model calculates an attention score for every possible pair of words in the sentence.
So if I have the sentence like, the bank of the river.
Right, the token for bank checks its query against the key for river, gets a massive attention score, and mathematically suppresses the conceptual vectors related to, finance.
Because the context of river overwrites the context of money.
Exactly. And it does this across billions of parameters in parallel.
That parallel matrix multiplication is exactly why we rely on GPUs to train these things.
Oh, absolutely. Without GPUs, we'd be nowhere.
Which leads us straight into the practical toolkit. Because understanding this conceptually is cool, but to actually start building, you need to know the industry standards. And if you're building this out, the undisputed interface of choice is Python. But I'll be honest, when you're dealing with advanced matrix math at this scale, Python historically isn't known for being, like, lightning fast.
No, it's definitely not.
It's interpreted, not compiled. Python is so accessible that it almost feels too basic for something as cutting edge as building an LLM. Is mastering Python really enough to rival what big tech is doing?
It's a common initial friction point for developers moving into AI. They think Python is too slow, but Python isn't actually doing the heavy lifting.
It's not.
No, it's just acting as the orchestrator. The mathematically intense operations, those parallel matrix multiplications we just talked about, they're written in highly optimized C++ and CD.
Okay. Executing directly on the NVIDIA GPUs. Exactly. Python simply provides an elegant, readable API to call those underlying C++ functions. So you get the developer velocity of Python without sacrificing the execution speed of C++ way.
Right. Which brings us to the frameworks that bridge that gap, specifically PyTorch versus TensorFlow.
The big debate.
Yeah. Looking at the landscape of advanced LLM engineers, there is just an overwhelming preference for PyTorch right now. And it's not just a syntax preference, is it? It fundamentally comes down to how the frameworks handle computation graphs.
That's the absolute crux of it. Historically, TensorFlow relied on static computation graphs.
Meaning you had to define the whole thing up front.
Right. You had to define your entire neural network architecture, every node, every layer, compile it, and only then could you run data through it. It was highly efficient for production, but nightmare for debugging.
Because you couldn't easily peek inside the network while it was running. It's just a black box until the compilation is done.
Exactly. PyTorch, on the other hand, popularized dynamic computation graphs, or eager execution.
Eager execution.
Yeah.
The graph is built on the fly as the operations occur. This means you can use standard Python debuggers, print statements, and dynamically change the architecture of the neural network during the forward pass.
Which is huge for experimenting.
Oh, for researchers and developers building highly complex custom transformer models, that flexibility is non-negotiable.
Okay, so we have Python and PyTorch as our fundamentals. But let's look at the reality for you, the listener, if you're a solo developer or a startup. You aren't going to spin up an AWS cluster and spend $20 million training a foundational model from scratch.
No, definitely not. You'd go bankrupt.
Right. You're going to pull down an open source model, like Llama or Mistral, and fine-tune it. But a raw pre-trained model isn't always useful out of the box for a specific business.
No, it lacks specific context.
Like if I'm building an internal tool for a law firm, I needed to access private case files, not just, general internet knowledge from Reddit.
Which is exactly where Retrieval Augmented Generation, or I, becomes the most heavily monetized skill in the current market.
Let's get under the hood of a RAG pipeline. Because I've got this analogy. It sounds like taking a brilliant but amnesiac professor, that's the LLM, and handing them a highly organized filing cabinet of your company's private documents, the vector database.
That is a perfect analogy. Because conceptually, you're taking your user's prompt, running it through an embedding model to turn it into a vector, and then doing a similarity search in that filing cabinet, a vector database like Pinecone or Chroma.
And then we pull the most mathematically relevant text chunks and inject them directly into the context window of the LLM.
That is the exact flow. And the reason RR is so vital is that it fundamentally solves the hallucination problem for enterprise applications.
Because it's not making things up anymore.
Right. You aren't relying on the LLM's parametric memory, the knowledge it baked into its weights during pre-training. You are using the LLM strictly as a reasoning engine.
You hand it the retrieved context and say, answer the user's question using only the data provided in this context.
Yes. It effectively separates the knowledge base from the reasoning engine. If a law firm updates its internal policies, you don't have to retrain the neural network. You just update the documents in the vector database.
It's so efficient. But here is the major hurdle, and this is the reality check. I can build that Python RH pipeline in a Jupyter notebook locally, like on my laptop, and it works flawlessly.
Of course it does.
But transitioning from my laptop to a live application where 1,000 employees are querying the database simultaneously, that's where a massive amount of developers just hit a brick wall.
Yeah, it's what the industry affectionately calls tutorial hell.
Tutorial hell.
The internet is full of developers who can build a local prototype. But real commercial value demands deployment infrastructure. It requires a robust deployment stack.
So let's break down the mechanics of that jump. What actually breaks when you move that Argot app from localhost to a cloud production environment? Why is deployment such a beast?
Well, everything from environment consistency to concurrency management breaks. When you deploy, you have to handle state. If 500 users hit your endpoint at the exact same millisecond, a basic Python script will bottleneck and crash immediately.
So that's why you need a high-performance web framework.
Exactly. Like Fast2PI to handle those asynchronous requests efficiently.
And then you have to containerize it, right? Because the dependencies for deep learning libraries are notoriously brittle. Like one wrong version of a package and the whole thing fails.
Yes, Docker is absolutely essential here. Docker packages your PyTorch code, your model weights, and the exact version of every library you used into an isolated container.
So it completely eliminates the, well, it worked on my machine problem.
Completely.
Yeah.
But Docker alone isn't enough for scale. If traffic spikes, one container will just get overwhelmed. That's where Kubernetes comes in.
The orchestrator.
Exactly. Kubernetes monitors your application. If it sees that your single Docker container is maxing out its CPU, Kubernetes automatically spins up 5 more identical containers.
Oh, wow.
It balances the incoming API traffic across all of them and then tears them down when the traffic subsides. It handles the load balancing and the pod failures dynamically.
I mean, I'm looking at these deployment requirements, and spinning up AWS instances with high-end GPUs seems like it would bankrupt a solo developer in a week.
It definitely can if you aren't careful.
Right. If you're building a SaaS product, say, a custom AI writing assistant, how are you mathematically shrinking these open source models so they don't eat your entire profit margin and cloud server costs? Why do businesses care so much about these optimization techniques?
Well, this is exactly why companies pay massive premiums for engineers who understand optimization. The 2 major levers you have are quantization and LoRi. Let's look at quantization first.
Okay, let's do it.
Normally, when a model is trained, its weights, the billions of parameters dictating its behavior are stored as 32-bit floating point numbers, FP32. That requires a massive amount of VRAM just to load the model into memory.
So we compress the math, we shrink the numbers.
We reduce the precision. Quantization mathematically maps those 32-bit numbers down to 8-bit integers or even 4-bit integers.
But wait, doesn't that inherently degrade the model's intelligence? If you're drastically rounding off the precision of its weights, surely the reasoning suffers, right?
You do lose a marginal amount of precision.
Oh.
But the fascinating part of neural network architecture is how robust it is to minor noise.
Interesting.
The degradation in output quality is often imperceptible to the end user. But the memory footprint shrinks by 70 to 80%.
That is massive.
It is. Suddenly, a model that required 4 A100 GPUs to run can be served efficiently on a single, much cheaper, consumer-grade GPU.
That completely changes the unit economics of a SaaS business.
Entirely.
Okay, what about fine-tuning? Because I actually do want to alter the weights of a foundational model to make it write code better or, I don't know, sound more like a specific brand. Fine-tuning a 70 billion parameter model traditionally requires a supercomputer.
Which is where LoRack comes in low-rank adaptation. If you want to update a massive model, traditionally you'd perform full fine-tuning, calculating gradients and updating every single one of those billions of weights.
Which takes forever and costs a fortune.
Yes. LoRa is a brilliant mathematical workaround.
I've always thought about Laura like learning to drive a brand new car. You don't need to relearn the fundamental concept of driving, steering, braking, navigating traffic.
Right, you already know how to drive.
That's your massive pre-trained base model, and you freeze it. You just need a tiny bit of new instruction on where the specific wiper controls and headlights are on this specific vehicle.
That is a highly accurate way to frame it. Mathematically, LoRa achieves this by injecting small, low-rank matrices into the transformer layers alongside the frozen original weights.
Okay.
Instead of updating a massive 10,000 by 10,000 weight matrix, LoRa decomposes that update into two much smaller matrices, say 10,000 by 8 and 8 by 10,000.
Oh, so you're reducing the number of trainable parameters from billions down to just a few million.
Exactly. You train just those small matrices, which you can often do on a single GPU in a matter of hours. When you deploy, you just multiply those small matrices together and add them to the base model.
Yeah.
It achieves nearly the same performance as full fine-tuning at a fraction of the compute cost.
So what does this all mean for you when we put the pieces together? You break out of tutorial hell, you build out your PyTorch pipeline, you optimize your open source model with quantization and LoRa so you aren't bleeding server costs.
Yep.
You containerize it in Docker, orchestrate it with Kubernetes, and deploy it to the cloud. You have moved from a consumer to an architect. And the payoff here is global earning potential, right?
The leverage available to an individual right now is staggering. If you look at current market rates on freelance platforms, places like Upwork or TopTal or specialized engineering networks, developers who can confidently build RAG pipelines and optimize custom LLMs are charging premium consulting rates, entirely remote.
From anywhere in the world.
$50 to $300 an hour is common.
And because the work is remote, you're seeing massive geographic arbitrage. Developers operating in regions with a lower cost of living are tapping directly into Silicon Valley budgets. But honestly, the highest ceiling isn't just trading time for money as a freelancer.
No, it's leveraging this stack to build software as a service.
Building a microsauce, that is where the scalability of everything we just discussed really shines.
Exactly. If you identify a specific niche, say automating initial legal discovery for boutique law firms, or building specialized customer support agents that actually integrate with a company's custom internal database, you build the RAG architecture once.
Build it once.
You deploy it on scalable cloud infrastructure, and you sell it as a monthly subscription globally.
It's the ultimate decoupling of time and income. And companies are actively looking to acquire these automated workflows. The market for AI automation agencies, businesses that go in, analyze a traditional company's pipeline, and replace their manual lead generation or data entry with optimized LLM scripts, is exploding right now.
It really is.
Yeah.
But there is a crucial caveat to all of this. If you are operating independently, you don't have a corporate marketing department backing you up. You have to be visible. You need to build a personal brand.
Right, building in public, committing code to GitHub, sharing your benchmarking tests on X, writing technical breakdowns on LinkedIn.
It acts as a continuous passive lead generation machine. When a CTO or a founder is looking for someone to optimize their infrastructure, they aren't looking at traditional resumes anymore.
No, they want proof of work.
They're looking at GitHub repositories. They're looking for developers who understand the friction points of deployment and optimization out in the open.
And what's wild to me is the timeline to achieve this level of competency. This isn't a 4-year degree path.
Not at all.
If you are deeply focused, the transition from basic Python knowledge to deploying AI architecture is measurable in months. It's so democratized. Like, spend 30 days deeply internalizing the math behind backpropagation and tensor operations in PyTorch.
Get the fundamentals down.
Then take the next 60 days to dissect transformer architectures and experiment with open source models like Llama locally.
And by the 3 to 6 month mark, you are entirely focused on building scalable RG pipelines and mastering that deployment stack, Docker, FastAPI, cloud environments.
And within a year, 12 months, you're positioned to either launch a scalable product or command top-tier rates as an independent architect.
It requires intense curiosity, obviously, and a willingness to break things in production. But you do not need permission from a giant tech gatekeeper to start your 30-day clock today.
Exactly.
The frameworks, the open source models, the documentation, it is all sitting there on the internet waiting to be utilized.
And the future internet economy over the next decade will be aggressively divided between those who just consume AI-generated outputs and those who actually architect the systems.
The builders will win.
They always do. Which brings me to a final thought I want to leave you with today. Something for you to mull over. We just spent a lot of time discussing how optimization techniques like quantization and matrix decomposition are drastically shrinking the physical memory footprint of these incredibly intelligent models.
Right.
If open source models like Llama or Mistral continue to get smaller, more efficient, and mathematically denser, what happens in a few years when every single solo developer has the processing equivalent of a 2023 big tech server farm running locally, natively on their laptop hardware?
That's a fascinating question.
When the friction of cloud computing costs approaches zero, how will that entirely redefine what we consider a small business?
I mean, it's going to turn single-person operations into entities capable of competing directly with multinational corporations.
Right.
The definition of startup is fundamentally changing.
It really makes you think. So if you're still sitting in the passenger seat of this technological shift, it is time to open the door, pop the hood, and grab a wrench. The engine is yours to build.